Good morning and a stellar welcome from the European Space Technology Center in Noordwijk, the Netherlands, on behalf of the European Space Agency. My name is Kai Nöske. I'm ESA's Communication Program Officer for Science, and today we are looking forward for the third data release of ESA's cornerstone mission Gaia, the billion-star surveyor that has taught us enormous amounts of new knowledge about our Milky Way, our home galaxy, the life and death of stars, and our place in the universe. Thank you all for joining us. Today we have an expert panel assembled, and to my right I'd like to welcome Josef Aschbacher, ESA's Director General. To my left, Günther Hasinger, ESA's Director of Science. From ESAC in Villafranca, Spain, Europe's Space Astronomy Center, Timo Prusti, the Gaia project scientist for ESA. From Leiden, the Netherlands, Anthony Brown, the Gaia DPAC, the Data Analysis and Processing Consortium Chair, Anthony Brown. And from the Istituto Nazionale di Astrofisica, based in Padua, Antonella Valenari, the Deputy Chair of the Gaia DPAC. Furthermore, we have Connie Ayres. Connie is a professor at KU Leuven and at Radboud University, a scientist who was the lead author of one of the key papers and will discuss some of the results that came out of the data release. Now, I would like to hand over to Josef Aschbacher, our DG, to give us an ESA perspective of the upcoming data release. Thank you.
So thank you, Kai, and very welcome also from my side. Today is really an exciting day because this data release has been waited for since a long time, and I've just had a discussion with my experts, with Günther in particular. 2 billion objects or stars are to be monitored, and the data of those are being released today. And this is really incredible because it will open the floodgates for new science and for new findings of our universe, of our Milky Way, and I think this is really fantastic. I'm a scientist myself, as you know, not an astronomer, but a geophysicist, but still knowing what it means if good data become available for science is always a very important moment, because this opens completely new dimensions of finding new results and really diving very deep into it and see what you can find and what new theories and new algorithms and new knowledge you can obtain from this data. So this is really a fantastic day for astronomy, for science, for ESA, but really for all in Europe. And let me just, with a few words of introduction, thank all those who have been involved in producing these data sets, of course the science teams themselves, but also the engineers who have been working on Gaia in the past to put the mission together, and our member states, because as always our science program is composed of different elements, and our member states are at the core of everything. First of all, they are funding ESA and the science program, but also they are contributing extremely important instruments or knowledge themselves through the research institutions, and of course industry, which is carrying out most of the implementation and development tasks. So really a big thank you from my side to the community which makes up ESA, and this Gaia mission being one of the core missions of the science program, and the science program being one of our backbones of the ESA activities. And this is really a fantastic day today. So thank you from my side.
Thank you very much, Josef. Günther, would you like to pick up the ball?
Thank you, Josef, for picking more or less, for sending me the ball immediately. So I'm indeed very proud to be directing the ESA science program, and the scientific program of ESA is indeed enabling scientists to take over leadership, technology, scientific leadership in a number of very important areas, from the solar system and the heliosphere to the galaxy, and then to the very far reaches of the galaxy and the universe. If I could show the slide with the fleet of the ESA missions looking at the universe, and you see as the different colors of the rainbow the different missions that we have, and in the middle row are the missions which are active right now: James Webb, Hubble, Gaia, and so on. And Gaia is basically in the middle of this map now and in the middle of our attention today. Thank you for the slide. Gaia is really turning the world in astronomy upside down. And the number of publications, as you may know, is skyrocketing. Every day, 5 papers for Gaia from Gaia missions are published. And in the last 3 years, we have actually overtaken the gold standard in astronomy, the Hubble Space Telescope, and are now producing about 1,600 papers per year. And just in time for our meeting today, there have been 2 major prizes that have been given out in the last 2 weeks for things that are also related to Gaia. So I'm very happy to congratulate Leonard Lindgren and Michael Perryman for receiving the Shaw Prize in Astronomy for the development of astrometry, and in particular the Hipparcos and the Gaia mission. And then I'm even more happy today to congratulate Connie Ertz, who we have here in our panel, Jørgen Christen Dalsgaard and Roger Ulrich for the Kavli Prize. This has been given for developing of helioseismology and astroseismology. It turns out that astroseismology is now also a very important element of the Gaia mission. And with this, I hope for a wonderful day of this data release and the splash of new results to come. Go Gaia, go.
Go Gaia, go indeed. And talking about catchphrases, you can follow this data release under hashtag GaiaDR3. You can follow on Twitter ESA Gaia, ESA Science, or ESA. And if you want to find out anything about this mission, you can go to our landing page, esa.int/Gaia. Now, to give us a rejoiner of this amazing mission, I'd like to hand the word over to Timo Prusti at the European Space Astronomy Center in Villafranca, our Gaia project scientist. Timo, please.
Good morning, everyone, also on my behalf. As it was already mentioned, Gaia is a mission by the European Space Agency with a pan-European consortium, DPAC, doing the data processing. Gaia is really designed to reveal the origin, structure, and evolution of our Milky Way galaxy. We can say that we know a lot about the universe as a big entity, from Big Bang, after a few seconds of it, what happens. At the other end, we also know a lot about our solar system, planets, asteroids, comets. But what we are actually lacking knowledge is our home galaxy, Milky Way. And that is exactly the puzzle what Gaia is going to fill. It's going to provide the information of our own home Milky Way galaxy. In order to do that, Gaia has to capture nearly 2 billion stars to measure their position, movement, and brightness. And the additional elements from this data, which are specifically in this Gaia Data Release 3, are the scientific products which are revealing the properties of these stars, temperatures, masses, composition, what type of objects they are, and much more. Let me go a bit back in time. Gaia was launched 19th of December 2013. The satellite was delivered to so-called Lagrange 2 point, which is very popular now for astronomical satellites. It's dark place, and we can observe the dark skies from there. Gaia has 2 optical telescopes, 3 instruments, and about 1 billion pixels to make all the measurements. As I mentioned already, most of the targets are stars, but Gaia captures as well objects in our solar system, like asteroids, and galaxies outside the Milky Way. And this release is really containing everything what Gaia has been measuring, a full set of data.
Thank you, Timo. That was a great overview of what Gaia has been doing, what Gaia is doing. And the other side of Gaia, aside from Gaia's home in ESA and home in the member states, is a unique collaboration, a remarkable collaboration of scientists who take care of the data that Gaia is delivering. And chair of the DPAC is Anthony Brown, who has promised to tell us something about DPAC and his work. Anthony, please.
Yeah, good morning, everyone, and welcome also on behalf of Deepak to this wonderful occasion to celebrate the third Gaia data release. So the effort to produce Gaia DR3 started just over 5 years ago when we ingested 940 billion observations of 2 billion sources into our data processing systems. And in December 2020, we already provided the distances, motions across the sky, brightness and color of the stars in the form of the early Gaia data release 3. And today we present the full Gaia DR3. It consists altogether of over 10 terabytes of compressed data for almost 2 billion sources, organized into roughly 90 tables, which present the richest set of astronomical data ever published. The first slide, please. The data processing itself is carried out, as Kai said, by a European consortium, the Gaia Data Processing and Analysis Consortium, in which over 20 countries and more than 100 institutes participate, including also contributions from several partners outside Europe. There are some 450 persons involved, including scientists, software engineers, and project management specialists. Thank you for the slide. Now, the Gaia collaboration has really worked very hard over the past 5 years to bring Gaia DR3 to you today, often combining their very busy Deepak schedules with other professional but also personal demands, in particular during the COVID times. And the pandemic has obviously affected the work done by everyone. And so I really want to thank deeply all the members of Deepak for the tremendous effort they made and all the time they put in this difficult and stressful period. And so I really think that the celebration of Gaia DR3 is very well deserved for everyone. Second slide, please. Now, I want to mention specifically one person, Dimitri Pourbet, who you see his picture here, and he sadly passed away last year. Now, one of the main new components of Gaia DR3 is the largest ever catalog of binary stars, superseding everything that was done in the past 2 centuries or so. And it was Dimitri who led this task from the very start of Deepak. So this release is really a testament to his leadership and to his efforts that he put in all these years into bringing about the wonderful binary star catalog that very soon our colleagues can start to enjoy. Thanks for the slide. Now, to close, as Günther already mentioned, it's an extremely productive mission. Many thousands of papers appeared which use Gaia data in some form or other, with topics ranging from the solar system all the way out to the distant universe. And I think for many of us, in particular for the younger astronomy colleagues, it's basically not possible anymore to imagine a time where you could not look up for every star, whatever you wanted to know about it. This is how much Gaia is embedded in the astronomy ecosystem at the moment. Now, the Gaia DR3, in supplement to what we already provided with Gaia EDR3, will really provide the same ease of access to the data, but then for looking up everything about the properties of stars that you want to know. And it's this that will really unleash the full power of Gaia. So I can really not wait to see the exciting results that all my colleagues will be coming up with after using the Gaia DR3 data. And I leave you with the message that what I think Gaia DR3 represents is really a supermarket of astronomical data that we will all enjoy in the coming years. Thank you.
Thank you, Anthony. Thank you for the emotional memory of Dimitri. Thank you for your summary. And I have to say, we really live in an age of big data astronomy. If the Deepak had, with a completely unemotional face, tells us they went through 930 billion observations to create a catalog of 2 billion objects, as it was the most normal thing in the world. Thank you. And we would like to move over to Antonella Marinari now, who will tell us about what we can expect from these data, what's in these data, and what kind of science we can look forward to. Antonella. Did we lose her?
We cannot hear you, Antonella.
Let's move forward. Beatrice, could you please try and reconnect Antonella? And in this case, we would move forward to Connie Ertz. Again, for those joining us late, congratulations for being the recent recipient of the prestigious Kavli Fellowship, the Kavli Prize, which is one of the most prestigious, one of the biggest awards an astronomer can receive for her groundbreaking work in astroseismology. And Connie will tell us now what astroseismology is about and what it means for Gaia.
Yes, thank you very much. Good morning, everybody, for your congratulations also that I received from so many people. But let me take this opportunity to tell you something about astroseismology. So most stars, including our sun, experience stellar oscillations. They are often termed starquakes or stellar vibrations. And so these vibrations make the stellar gas move up and down, and it changes the brightness of the star as a function of time. So it makes the stars blink in the sky. And this blinking of the stars, well, it can happen with amplitudes, let's say, of parts per 10 up to parts per million. So this depends very much on the mass and the evolutionary stage of the star. Now, blinking stars do offer astronomers a very powerful tool to study their internal physics and chemistry. Huh? Think of earthquakes. You all know that seismologists love earthquakes if they're not too violent, so to speak, because these allow us to understand what is happening inside our planet. And so astroseismologists actually do the same, but then for stars. So we use starquakes to deduce the internal temperature, the density, the materials inside stars, and above all, also the interior rotation of stars. Now, Gaia was not at all designed to study starquakes. It can also not do it for stars like the sun, because the sun and solar type stars have too small quakes. But it turns out to be a champion of detecting starquakes in hot, massive blinking stars. Gaia DR3 already allowed us to detect more than 100,000 of such blinking massive stars. And many of them rotate so fast that the Doppler effect shifts their frequencies into new regimes for us to study. Now, think of an ambulance. You all know that when an ambulance approximates you as an observer, it shifts the frequencies of the sound waves to higher values as the star approaches you. And so we can actually detect this in starquakes that's happening while they rotate. So this is a fantastic machine. Now, to give you some better feeling of this, we will now look at an animation and listen to some sound of commonly detected starquakes that Gaia detected. And now some real stars. Listen carefully.
Amazing.
Okay, so thank you for showing the animation and the sonification. What you just saw and heard were first 3 dipole modes, then 5 quadruple modes, of which the middle one was each time placed with sound. Now, human beings cannot hear the true frequencies of these oscillation modes. So we artificially multiply them by a big factor, 8.6 million, to bring them into your audible range of your ears. And the last 3 stars that you saw and heard, the blinking of the surface, was actually representing 3 stars where we analyzed the Gaia DR3 data, and we were able to detect the dominant quake of these stars. And so Gaia can detect star quakes provided that they have an amplitude above parts per thousand. That's currently the limits that we are facing. Above all, Gaia was not made to do this, but it can detect the dominant starquake. Now, Gaia alone does not allow us to do astroseismology because the data is simply not fast enough. On the other hand, Gaia has already allowed us to detect thousands and thousands of new blinkers with gravity modes that are rotating fast. And so, along with Gaia's luminosity, which is a unique feature delivered by the satellites, Gaia does tell us where the most promising stars for astroseismology are in the galaxy, 100,000 of them. And so what is nice about Gaia is that when we use these Gaia data in tandem with specialized infrastructures, such as the TESS mission that is now ongoing, that's NASA mission, but above also the future ESA Plato mission that will be dedicated to study or to detect many, many starquakes. When we use Plato in tandem with Gaia, we have a fantastic new gold mine to do astroseismology of hundreds of thousands of stars in our Milky Way galaxy. So for us, this is really a wonderful day now that we have the time series to dive into them and study the dominant starquakes of so many stars in the galaxy. Thank you.
Thank you very much, Connie. Now, Antonella has rejoined us. Apparently, she has some connection problems. Antonella, are you able to talk to us? Can you hear us? Can we hear you?
Good morning. Can you hear me?
Thank you.
Yes.
So, good morning to everybody. For a few information concerning the stars in our Milky Way, for 2 billion stars, we deliver an incredible amount and quality of information. We have a catalog of binary stars that is 40 times larger. That is what is already available in literature. Concerning binary variables, we have 10 million stars, and you already heard from Connie very interesting results. From the low resolution spectra, we were able to derive stellar parameters like temperature, mass, age of 500 million stars. And from the high resolution spectra, we were able to derive an additional component that is the chemical composition of the stars. Next slide, please. In the slide that you will see now, we have a few highlights. This is the most complete full sky map of the radial velocities in our Milky Way. It contains 33 million stars. You see in black all the stars that are moving towards us, and in yellow reddish the stars that are moving far away from us. So you clearly see the rotation of our disk. And the two arrows are showing the galaxies that are satellites of our Milky Way and that have a peculiar motion, like the Magellanic Clouds with the black arrow and the Sagittarius galaxy with the white arrow. And the information, if we add the information about the proper motion, we will be able to have a 3D mapping of our galaxy, of the way in which our stars are moving in our galaxy. Next slide, please. The second highlight concerns the chemical composition from high resolution spectra. You see here the density of the stars that were measured in this way. You clearly see all the stellar component of our Milky Way. So you have the disk, the central bulge, the blue halo around. In the next slide, you see the same map, but in chemical abundances. You have in red the high metallicity stars that are part of our disk, and in blue the low metallicity stars that are in the outer disk and in the yellow. So this is the information about the motion of the stars and the chemical composition is fundamental to derive a family tree of our galaxy. So to understand which stars are born in our galaxy and which stars instead were born in external galaxy, then merge with our galaxy. This is an incredible gold mine for astronomers. Thank you.
Wonderful indeed. So while we are still on track for the 12 o'clock Central European Time data release, the weather looks fine, upper winds are fine, the servers are up and running, and the data lines are open. I would like to go around the table and ask everybody about a fun or impressive fact that is their favorite fact to talk about. If you're on an elevator, if you're talking to two relatives at the dinner table, what Gaia is about. Timo, would you like to start?
I always like to make a connection with Gaia data to something called stellar occultations. We can now make such a good prediction of the star positions that we can predict a star shadow on Earth. And we can put a telescope to observe the shadow crossing the Earth. And you can imagine that the shadow from an asteroid caused by a starlight is incredibly difficult to predict. And we have some scientific measurements which are telling us new things of double asteroids or the atmospheres of moons around planets. And this is a sort of very niche topic of Gaia. It always appeals very fascinating to me that this is possible.
Thank you, Timo. I just learned something new. Anthony, would you like to follow up?
Yes, so Timo mentioned the occultations. That's indeed a very fascinating subject. And that brings me to what I actually like most about Gaia when I try to explain to people, you know, why am I staring at stars for 10 years and tracking their positions on the sky? And it's these very precise star maps that allow these better explorations of our solar system, but also navigation of spacecraft in the solar system. The New Horizons mission is a good example of that, who used the Gaia data to steer the spacecraft from Pluto onto the other Kuiper Belt object, Arrokoth. And of course, the tracking of the stars, measuring their distances, motions, but also their properties, is ultimately what allows us to look more than 10 billion years into the past history of our own Milky Way, all thanks to just very precisely mapping where stars are and what their properties are.
Antonella.
I always find very exciting when I have to talk about Gaia to my friends to explain that our galaxy is indeed a living entity where the objects are born, where they die. That our galaxy is in connection with the rest of the surrounding galaxies that are continuously interacting with our galaxy and sometimes also falling inside it. I think that this is something that is extremely fascinating.
Thank you. And Connie, aside from the sparkling stars you study, what else makes Gaia sparkle for you?
Well, let me stick to the blinking stars because that's really my pet topic, but hook on to what Anthony just said. It's the really high precision outlook for Gaia that will bring us 10 years of data potentially. And you know, for us astroseismologists, the precision of the star quakes of their frequencies goes as 1 over the total time base. And imagine we have that for 10 years Gaia, and we can couple that to the Plato mission that will be launched in 2026. That will be wonderful. For me, that duet is really an outlook into the future. I'm very much a future emphasis person, so I really look forward to that.
And thank you for advertising our future mission. Josef, you may have a geologist, geophysicist.
Yes, in fact, I was warned about this fun fact thing. So as I'm a geophysicist, I want to merge geophysics with astronomy. And what I show you now is something very special. You see here, there's a cup of a coffee cup where you can put tea in or whatever you want. What I've put in is sand, actually from the beaches outside here in Aztec. And there are grains of sand. So now imagine that each of these data which are being released now is 1 grain of sand. How many cups of coffee you think are being filled with this data which we are releasing today? And if you add it up and do simple mathematics and a bit of assumptions of how many grains fit in a coffee cup, you will have 500 of those cups filled with sand, which is the equivalent to all the data released. So I think this is quite impressive, and I'm very happy I can merge geophysics with astronomy.
Günther, would you like to close the circle with another cosmic perspective?
Yes. Actually, this is a real fun fact that you may have heard about, but You know that Gaia and James Webb are similar in the same L2 region. They are not on exactly the same orbit. They move around L2 in different ways. And actually, every once in a while, James Webb is visible in the Gaia field of view. And so we have, a few months ago, released a picture postcard where Gaia was observing James Webb. And this was not just fun. Actually, it turned out that the position where Gaia found James Webb was about 40 meters away from where James Webb thought it would be. And therefore, Gaia can actually tell James Webb better and more accurately where it is than James Webb itself. And so we want to continue this monitoring. We want to measure the position of James Webb through Gaia. But then also James Webb has said that at one point they would do a reciprocity. They want to look at Gaia with the James Webb telescope. So I'm looking forward to that.
So we're sitting outside 1.5 million kilometers from Earth, both of them in a halo orbit of about 800,000 kilometers around L2, going around the Earth, around the sun with Earth, and they're telling each other you're 40 meters off. Also, hats off to the colleagues in operations who know exactly where probes are with about this accuracy. It's amazing. Josef, a closing question to you. Looking at the success that I think we can, without bragging, say this mission has been, what does a mission like Gaia mean for ESA, for its member states?
I mean, what does it mean? So first, Gaia is a mission that is a full ESA mission, full in the sense of course, the member states are funding the science program and therefore the Gaia mission, but also the design, the development, the launch, the operation, all done by ESA through our partners. And I think this is something where all of us, really all of us, can be extremely proud. And I was really so impressed to hear the reports of the scientists. I mean, fantastic. Timo, Anthony, Antonella, and Connie about the earthquakes or the space quakes or astroseismology, as it is called, is really fun. It's really amazing and it's really fantastic. So this for me means really so much. I think there's so much exciting science coming out of it. I'm really impressed of what I've just learned myself today. I've really seen some extremely impressive things, and but I'm also realizing how many people are involved in making this happen. People in the member states, science labs, science groups. Connie having received the award today. Congratulations also from my side, but also many others who are working day and night in order to make this a huge success. So I'm just so impressed and also humbled by all this excitement and this intelligence which is brought together here, from science to engineering, and to really make this data release possible. So for me, this is really is very remarkable. I've already mentioned before the thanks to the member states, to all the people involved, and I really would like just to reiterate this, because this is at the core of how we function as ESA. We have a very important ministerial coming up in November. The science program is a key element of it, and whoever is watching here making decisions about this, I can only reiterate how important it is to fund the science program well, because this is what we need. And in order to have exciting moments like this, we do need the support of our member states and the community at large. So really big thank you from my side, and very impressive what I see.
Thank you. Günther, talking about the future of the science program, will there be another Gaia?
That's a very good question. First, I would like to mention one mission which was not mentioned today, which is Euclid, because Euclid is not measuring stars, it's measuring galaxies, but you can in principle regard it as a Gaia for galaxies. And when you look at the Euclid data, it will actually outshine the Gaia data by another factor of 5 to 10. So there will be more data, a tsunami coming towards us. And so we are actually learning a lot from the Gaia Deepak, how we will deal with the Euclid data. Now, indeed, the question of whether there will be a successor to Gaia as such is a very important one. And our Voyage 2050 exercise, which is looking at the next 25 years of the ESA science program, has made Gaia in the near infrared a very high priority mission, which we hopefully can implement. I mean, we have to talk to the scientific community, to the member states. But if you imagine Gaia will stop working in a few years, then we will not have any more new data. In the meantime, the stars are continuing to move. And so year by year, our knowledge of the stars will actually degrade if we don't do anything. if we could do another Gaia about 10 years later, then we could tie these two together and we would get even more accuracy of the proper motions and the stellar velocities. And this Gaia in the near infrared would then also be able to peer into the dark regions of our own galaxies. We'll be able to see the galactic center, and we'll probably see not only 2 billion, but probably 10 billion stars, because the infrared stars are more, there are more of them and they are shining brighter in the infrared. So indeed, I think Gaia has set the pace to another future for a whole generation, hopefully in 20, 25 years from now.
Let's cross our fingers for, and already say, go new Gaia. Thank you so much to this very entertaining, very knowledgeable panel. We'd now like to open the question to the attending journalists. And please shoot from the hip. Bea, do we have, can you put questions through to us, please? Seem to have a technical problem here. Leanne, could you possibly try and take over? I'm not seeing the questions coming through, I'm not seeing the speakers, I'm not seeing the journalists unmuted.
I do not see any questions at all in the chat.
No, neither do I. In theory, Martin Stepanek, are you unmuted? Could you please introduce yourself and the news organization you're working for? At this time, we cannot hear you. You have to unmute yourself once you get the trigger message in the chat.
Can you hear me?
Yes.
Okay, so I just wanted to know, because you spoke about the future of Gaia. Do you want to have more actors in these Gaia missions, or do you want just to stay with the same collaborator? Because I think that could be a great idea to try to expand it. So I just wanted to know, what did you plan to do for it?
This is from Kesako Podcast. And could you please name your name as well?
Maybe that's a question for Anthony.
Okay, so here's my microphone. So my name is Sarah Ginan.
Thank you, Sarah.
Thanks for the question. So if I understand correctly, you are asking whether we would expand the collaboration beyond Europe for a follow-up Gaia mission. I, in principle, see no reason why not. Of course, this is something that hopefully can still be completely led and done by ESA. But also already in the Gaia mission itself, we have a few contributions from outside Europe who are, very valuable contributions. And I think a similar formula will work just as fine for Gaia Near.
Anthony, I understood the question such whether we want to expand the existing Gaia consortium in the future even with the existing Gaia data.
Whether we want, the Gaia Near would still be some time off, so we'll have to invest in making sure that there is a consortium in place at the time that can take over. Of course, a number of us can continue, are young enough to still be there when the new mission flies, and we should certainly capitalize on the expertise. But definitely, we will need new people to drive this.
Thank you. Then we have a question from Martin Stepanek.
Oh, can you hear me now?
Yes.
So Martin from Der Standard in Austria. I have a question about this big data thing, because obviously we need more data and everything is great, but are we reaching sort of a point where it's becoming more and more difficult to kind of handle the data? Like what kind of challenges do you see for the future in sort of finding that one particular data we need?
Timo, would you like to answer that?
Yes, I can try to outline a little bit what the issue is. Indeed, the more data, it is more difficult to handle, and as we know, there are a lot of technological advances of how to process data quicker. And I think what we are going to see in the future is that there is always some ways a bottleneck. I would say that at the moment the bottleneck is to move the data around. And we are looking for solutions to how to handle that one. So I think it is also driving the innovation of how to deal with the data. The amount of data is needed for the science, and we will find the technical optimum solution as we go. I think Euclid is, as already mentioned by Günther, Euclid is going to make a challenge with even more data, and they are tackling it. So we are keeping in pace with coping with the speed.
Maybe, Timo, I can add there, maybe instead of bringing the data to the scientists, we are thinking of bringing the scientists to the data. So we will basically open computers with some special workplaces where the data are, and the scientists can log in there, so that only a subset of the data needs to be transferred. That is one of the possible solutions. And then the other solution is clearly artificial intelligence to try to dive through the data more mechanically to find exciting stuff.
Thank you.
Thank you.
Next up, we have Alex Wilkins, followed by Paul Woods. Alex, can you unmute and can you talk to us?
Thanks so much for the great press conference so far. My question pertains to starquakes. So something that has been said about these starquakes is that Gaia wasn't originally designed to detect them. And I was wondering, why is it that we can now detect these starquakes and we weren't originally supposed to see them? Is it the fact that we've made all these repeat observations? Why is it performing so much better than we thought it would?
Connie.
Well, I guess that's for me to answer. Thank you for the question. So it's not that we hadn't anticipated Gaia would not be able to do this, but the DR3 is unique because it now gives the time series photometry. And so for the moment, we see that the data have typically between 20 and 50 points per star, which for us seismologists is very few. But even that is enough to determine the dominant starquake, provided that it is above parts per thousand. Now, there are also instrumental effects at that level of precision. This is normal. That's what the mission was made for and how it got calibrated. And the neat thing is that now we have plenty of stars that have been previously studied with lower amplitudes, up to micromagnitude, as I said, or parts per million. Yeah. And these stars can be used as calibrators to help Gaia do a better instrument calibration in the future. And as I was alluding to, the longer we observe with Gaia, the better we can have an interaction between astroseismologists and Gaia scientists to optimize the mission calibration on the one hand, and to help the seismologist with the identification of the dominant starquake in those stars. So this is really a nice interplay. And it's now coming to fruition for the first time because we now have the time series photometry. And it will gradually become better and better and better in detecting more and more starquakes of these fast rotating blinking stars. So this is really exciting for us to look into the future. Yeah.
Thank you very much. And we have two connected questions that take us into the fascinating world of extrasolar planets. One came from Paul Woods of Nature Astronomy, asking about the exoplanet candidate detections. Gaia has detected some. What can we expect along the lines of exoplanets from Gaia in the future? And more specifically, Clive Cookson asks, how many exoplanets are there? How many stars are there in the galaxy? 100 billion, 200 billion? And whether Gaia is able to tell us where the exoplanets are in the galaxy through their effect on the movements of stars. So maybe that's again for Timo, because Anthony, you answered about what can we expect about exoplanets and what will Gaia tell us about them?
Yeah, I started answering in the chat. Yeah, so there are actually 2 exoplanets confirmed that Gaia discovered, both with the transit method. And we have in this release about 200 candidate transiting exoplanets. So those are all still to be confirmed. So I hope this is something the community will quickly pick up. We've also astrometrically detected exoplanets. I think there's a few tens or so again to be confirmed. But we expect that in the next release, DR4, there will be many more exoplanets. And in principle, Gaia, especially when it goes on for the full 10 years, should be capable of detecting tens of thousands of exoplanets down to Jupiter mass, roughly. And the great thing of Gaia, of course, is that it can scan essentially all types of stars for planets. So it will be a very complete survey in that sense. As to how many stars there are in a galaxy, we think somewhere around 200 billion, but that's a somewhat uncertain number. And with Gaia, we will get certainly better statistics on how many planets there are. But how that will affect the motions of the stars, I guess that will depend a lot also on, are there many free-floating planets out there? These are very difficult, of course, to see with Gaia. So that's something I cannot really say much about.
Thank you. And the floor is still open. We have a couple more minutes. We will not go to the full top of the hour. We would like to close no later than 10:55, since across Europe there will be about 20 events, regional and local events, national events in member states taking place, organized mostly by DPAC, by the scientific community around Gaia. And as a reminder, if you would like to follow, many of these events are also live streamed with more in-depth scientific talks. If you would like to continue following this data release, many things that it tells us, the press release just came out, the ESA press release just came out, the different publications on scientific papers on the release itself came out by the many partner institutes and associations of scientists. To follow on social media, to search on social media is hashtag GaiaDR3. You can follow the mission on Twitter at ESA Gaia, our webpage at ESA for Gaia at esa.int/Gaia. You can also use your favorite search engine to look for Gaia DR3, which takes you to the cosmos.esa.int webpage that has details on all the events, on all the papers, and any in-depth information on the data release. Next up would be Frank Jordans from AP. Associated Press, can you...
To doing this. I'm going to be a little greedy and ask two questions. The first one to Timur. Could you explain to a layperson, because some of us write for people who don't have a science background, why it is that having so much more data is useful? I mean, is it because you're looking for the needle in the haystack, or is just having so much more information going to add another realm of sort of insight into our understanding about the Milky Way? And for Antonella, am I right in understanding that the papers published so far have only come from the 450 members of the collaboration, or are there also papers from people outside?
Shall I take first the data amount question? So often I was mentioning that Gaia is observing almost 2 billion stars, so it is a lot. And people are asking, don't you manage with a little bit smaller amount? But as soon as you tell that this is about 1% of the Milky Way, it immediately turns the question upside down. They're saying, is it enough? Can you actually deduce what the Milky Way looks like with when you are only observing 1% of the stars? So I think we are there striking a balance. We try to have a reasonable sample, and indeed, there are some very rare objects which you have to observe a lot of objects in order to get the needle in the haystack. But just statistically, I think it is quite understandable that with 1%, it's not really that big fraction of the Milky Way. It simply is a very complex system.
Thank you. Antonella, that's the second part of the question for you.
Yes.
And another comment.
Yeah, so basically the data, the Gaia data are made publicly available to the scientific community as soon as they are ready. The paper that we have published, but the data processing is extremely complex. It involves a lot of technical details and a lot of information. And the paper that we have published up to now are basically describing just the way in which we have produced the data and the way in which we have checked that our data are fine and are suitable to be released to the scientific community because they are of scientific quality. We expect that now that the data are public and the scientists can look into this, we will have a lot of more papers coming from the scientific community exploring in details all the scientific content of this data.
Thank you.
But if I can quickly add to that, just to be very clear, the vast majority of papers that are published from Gaia, the many thousands, come from the full astronomical community, not just from the DEEPAC consortium. Obviously, a lot of us are involved in doing the science, but as Antonella said, the data is always immediately made public without us having a proprietary period, if that's what you were asking.
Clive Cookson, you still have your hands up. Was your question answered earlier, or did you still have open questions for us? Seems to be okay. It was answered, thanks. So, do we have any more questions?
Maybe can I give another answer to the first question,
Absolutely.
which Anthony has and Timo has already addressed quite well. But I think I understood the question is such: why do you need so many data? I mean, Timo said, okay, 1% is a very small fraction of the whole galaxy, and it's too little for us. But for the layman, why do you need 2 billion? Why don't 200,000? Why are they not sufficient? I mean, Timo basically already said the needle in the haystack part is one aspect, but the absolute precision that you get by adding many accurate data can lead to basically unparalleled things that you never thought before. Like, for instance, we can, with all the Gaia data together, we can now measure the way the Milky Way is actually throwing the solar system around. I mean, we can see the solar system is moving in one direction, but it is also accelerated away into its orbit around the galaxy. So there are tiny effects that is only one effect that you can measure if you are putting 2 billion information together. And I believe this is, so it's not just the sheer number, it is that it is enabling things that would never be possible without this large number of data.
Thank you. And if you have further questions, especially to the journalists, if you have further questions you would like to ask our experts or requests for interviews, please send them to media@esa.int. As usual, your one-stop shop for all media contacts. Wishing you all a great data release. Thank you very much, everybody, for watching. Thank you to our expert panel. Thank you both for joining us here at ESTEC. And I would like to wish us all a stellar, sparkling, 2 billion bright sources in the sky day. Thank you also to the community who contributed to everything. Have a nice day on behalf of the European Space Agency. Goodbye.